Hello, welcome to Introduction to Composites. Today is the last day of this week, and what we will do today is we will discuss the maximum work theory, or the theory from Sahil, which is used to predict failure of unidirectional lamina under plane stress more accurately relative to other theories, and we will discuss some of its finer aspects. And the most important thing we will discuss in that context is the direction of shear stress or the shear strain, and how it influences the strength of the material. So, once we go through this, it will become very clear to us that we have to be very careful while considering the direction of shear stress as we are calculating the parameter and trying to figure out whether the material is going to fail or not. So, first we will discuss the basic thinking as to what we are trying to state. So, let us write down the relation for failure, for the failure criteria. So, it is sigma L divided by sigma Lu prime minus sigma L divided by sigma Lu times sigma T divided by sigma Lu plus sigma T divided by sigma Tu whole square plus tau Lt divided by tau Ltu, and this number, as long as it is less than 1, the material is not going to fail. The material is not going to fail. Now, let us consider two scenarios, and these are simple scenarios, but that will make the things clear. Case 1. Okay. In the first case, we have two situations. So, this is situation A and there is another situation B. So, in the first situation, the fibers are oriented like this, and in the second situation also the fibers are oriented in the same way. Okay. So, in both the cases fibers are oriented in the 0 direction. The only difference in these two situations is that in the first case I am applying my shear stress in a positive way. So, this is positive shear stress. So, this is tau xy is positive, and in the other case the shear stress is negative. Now, in both these situations, physically when you look at it, what is the shear stress trying to do? The shear stress on the top surface is trying to remove the top layer with respect to the layer just below it, right. This top layer, it is trying to remove this top layer with respect to just the layer below it. That is what the shear stress is trying to do. Same thing this guy is also trying to do. So, so this is what it is trying to do, okay. And the same thing is happening in the other situation, and the resistance from the material because of its stiffness is going to be the same. So, in case in the first case, this situation and this situation will not give us any different results, okay. They will both fail at the same value of tau xy. Look at the relation for Sahil. If I look at both these cases, sigma L is 0, sigma t is 0. The only thing which is non-zero is tau LT, because tau xy is same as tau LT, right. Tau xy is equal to tau LT and sigma L is equal to sigma t is equal to 0 for both cases. Okay. So, what that means is whether the shear stress is positive or negative, if the failure shear stress will be same for both the situations, because I have a square term here. So, then right, so it does not matter. Next, look at case B, and this is where you will see the difference, case B. So, here also we have, oh I am sorry, it is not case B, case 2. And here we have two situations. In the first situation, we have fibers oriented at 45 degrees, and in the other situation also fibers are oriented at 45 degrees. In both the situations, fibers are oriented at 45 degrees. So, theta is equal to 45, theta is equal to 45. In the first situation, we are applying a positive shear stress. In the first situation, we are applying a positive shear stress, and in the second situation, we are applying a negative shear stress. So, here tau xy is positive, here tau xy is negative. Tau xy is positive and tau xy is negative. Now, in both these cases, I can also resolve these shear stresses in the LT plane, and I can redraw these pictures in the LT plane. Okay. So, here the shear stress is in the y direction, in the xy plane. I can resolve this and I can make another picture where I depict, instead of tau xy, I depict sigma L, sigma t and tau LT. Okay. And I can actually calculate those values by the transformation relations, but physically also we can see what is going to happen. So, if I have to make an LT plane, then the picture will look something like this. Okay. So, this is my direction of fiber. So, essentially what I am doing is I am taking a small cross section of this and I am cutting it like this, and I am measuring, trying to calculate what are the stresses in these directions. Okay. This is, so it is the same sample, but it is just a different way of looking at things. So, if that is the case, then what I see is that the component of this force tau xy on this plane, it will be in this direction, and the component, and of course, on the negative side it will be on this direction. Similarly, the component of the shear on the top, it will be what? In this direction, it will be in the compression direction, and it will be like this. Okay. So, this will be sigma L and this will be sigma t. Okay. In the second case, when tau xy is negative, we do the same thing. So, again we cut a small portion and see what kind of stresses are in the L and T directions, and let us see how they look like, just based on, and we can actually calculate using the relations we have developed, but we do not need those relations. So, this is the direction of fiber. and when you look at the shear stress on the positive surface, shear stress on the positive surface is going in the negative x, in the minus y. So, its component is going to be compressive in nature, and on the opposite side, I mean, same thing will happen, right. Similarly, the top surface, it will generate a tensile stress on these two surfaces. So, here sigma L is compressive and sigma T is tensile. Okay. Now, when you look at these two pictures, what is it that you see? Which one is going to fail earlier? Here, because I am pulling in the tensile direction, the chances, see here I am compressing in the transverse direction. So, the chances that it will fail very early is very less, but here because the fibers are like this and I am in the transverse direction, I am pulling, and we know that failure in the transverse direction in the tension because of tension is very less. So, this can fail much earlier, and the first situation will fail later, because of the role of sigma t, because typically sigma t u is much smaller than sigma t u prime. Let us look at some of the numbers which we had cited earlier. For instance, we in one example we said that, for instance, in this composite, look at this, sigma t u prime is 610 MPa, but sigma t u is extremely small, 72. So, the point what I am trying to make is that in the transverse direction, the tensile strength is extremely small. So, the strengths, if the shear, if the direction of shear changes from positive to negative, it can have a very significant impact on the strength of the material. So, we will make this thing a little more clear by doing an example. And these effects of the direction of shear become very important, especially when theta is not equal to 0 degrees. For theta equals 0, as we discussed earlier, it does not really matter, but when theta is non-zero, then it starts having a very significant influence. So, the example we are going to say is that sigma Lu is 500, sigma Tu is 5, tau Ltu is 35, sigma Lu prime is 350, and sigma Tu prime is 75. So, these are the material properties, okay. And the question is, and theta for purposes of simplicity is 45 degrees, and so we have a composite specimen like this. The fibers are oriented at 45 degrees angle to the x axis, and all the only load on the material is tau xy. So, tau xy is the only load. So, this is case A, and in the other case, so here the shear stress is negative, okay. So, the question is calculate tau xy max for cases A and case B. What is the maximum shear stress this kind of a material can handle? Okay. So, first we will do case A. So, what we have to do is we have to first calculate in terms of tau xy, sigma L, sigma T and tau LT. Okay. So, case A, theta is equal to 45 degrees, and so with that sigma L is equal to tau xy, right, because it is tau xy cosine square theta. Okay. And this is sigma T is equal to minus tau xy, and tau LT is 0. So, you do the calculation sigma L is tau xy divided by 500 square minus tau xy square divided by 500 times 350 plus tau xy square divided by sigma Tu square, which is 350 plus 0. Okay. And for failure this should be equal to 1. So, tau xy works out to 75.36 MPa. So, this is for case 1. Now, in case B, theta is equal to minus 45 degrees. So, sigma L is equal to minus tau xy, sigma T is equal to plus tau xy, and tau LT is 0. So, we again do the thing. So, tau xy by, so instead of 500 now I have 350 square minus tau xy square divided by 500 times 350 plus tau xy square, and this one makes a really big difference, divided by 5 square, and this for failure should be 1. So, tau xy max is equal to 5 MPa. Theta is minus 45 degrees, or you can say theta is same, but tau xy is negative of tau xy, it is the same thing. Okay. So, you get 5 MPa. So, the point what I am trying to make is that just by change of the direction of shear it can have a very significant impact. So, we have to be really careful in understanding what is the exact direction of shear, because intuitively we do understand tension is positive, compression is negative, but shear we do not differentiate the direction of shear a lot of times, but in this case the direction of shear is extremely important. So, this concludes our discussion for this week, and also whatever we have tried to cover, we have covered it. Starting next week we will develop an approach, so as to how to analyze the strength and failure of composite materials with several layers. But till so far we have been dealing with only a single layer. Next week we will start dealing with several layers. So, that concludes our discussion, and I look forward to seeing you next week at the same time. Best of the weekend and have a great weekend. Bye.